Alright, this is lesson 6.2 of AP Calculus. We're going to be talking about inverse trig functions today, and of course, its derivatives and integrals. So if you think about what we're talking about in inverse trig functions, I hope you can remember what trig functions look like and are written like. Sin x, remember that one? Yeah, it looks like this, right? And of course it continues on and on and on. Then of course there was cosine x. Alright, like that. Continuing on and on. And then there was tangent x, which was the graph that looked like this with asymptotes at pi over 2 and negative pi over 2. Of course that also went on and on and on and on. So, what are inverse trig functions? Well, you've seen them before. It's on your calculator. The inverse function uses the notation sine negative 1x. Now, in calculus, that negative 1 as a power seems confusing, so people then call it arc sine. So when you see arc sine of x, that's the same thing as inverse. Arc cos is the same thing as cos inverse. Arc tangent, once again, is the inverse of tangent. And that's why you see this type of notation here, here, and here. Okay? Now, we'll talk about this domain and range value in a sec. I'm going to ask you to turn the page, because on the next page, I want you to actually graph out the inverse trig functions first. Okay? So I gave you a graph of the regular trig functions. I guess I should have just written it on this page. Oh well, I can do it again. Right. And then tangent. And now the question is, how do I graph out the inverse? Remember back in pre-calc 12, the inverse is just the switching of the x and y values, or a reflection of the graph in the line y equals to x. So if I were to take that sine x graph and graph out the inverse or arc sine, I hope that you'll be able to see that the graph looks something like this. So there's 0, and it looks something like this, and it go on like that. And of course it go on like that as well. Okay? The arc cosine graph, very similar. So starting at 0, 1, now it'd be 1, 0, and here we go. It would look probably something like this. Right? On forever. And tangents, well, notice it goes from negative pi over 2 to pi over 2, and I think the graph would look something like that. Okay? Now, notice that one of these graphs is a function. That's this one. Yay! But the other two are not. So the question is, we need to be able to restrict the values on the range, the y values, to ensure that the function exists, or the graph looks like a function. So notice the domain values are always between negative 1 and 1. But if we want to restrict the range, it looks like for the arc sine graph, I want to keep this part here. Okay? If I kept more like over here, the problem once again is that vertical line test. Sorry, it cuts through two parts. That doesn't work. So once again, we need to just focus on the part of the graph in blue, which means arc sine has a range from negative pi over 2 to pi over 2. So I'm just going to give you a note here. Note the range. It's from negative pi over 2 to pi over 2, and we can include the end values. For arc cos, however, notice I can't just do that same part because look, oops, what did I just do? I can't do negative pi over 2 to that because look, the vertical line test doesn't work. So by convention, we just use this part here. So the range for arc cosine is actually just from 0 to pi. Okay? And arc tangent, well, the range, of course, is from negative pi over 2 to pi over 2. And that's what I wanted you to see here. This here is a geometric representation of the range values of each inverse trig. Notice arc sine goes from negative pi over 2 to pi over 2. Arc cosine is the different one that goes from 0 to pi. And arc tangent is just like arc sine. Okay? So there's your introduction to the inverse or arc, sine, cosine, and tangent functions. Let's just do some quick calculations before we actually even do some calculus. So evaluate without a calculator. Remember those special angles you should have remembered? So once again, arc tangent is really just inverse of tangent like this. And from your math, what, 10, 11, 12 days, I hope you remember that this is just the angle pi over 4. Inverse cos of negative 1. So what's the theta that gives you negative 1 on the cosine graph? I hope you know that that's pi. Ooh, negative root 3 over 2. Root 3 over 2 special angle, I believe, is pi over 3. Since it's negative, we can say this is equal to negative pi over 3. Okay. Or, of course, you could have used, remember, all students take calculus. And therefore, the answers would have been the third quadrant, which would have been 4 pi over 3, or the fourth quadrant, 5 pi over 3. Those are all acceptable answers. The last one, arc sine, is 2. Well, remember, 2 is outside the domain of negative 1 to 1. So therefore, this does not exist. Okay. Example 3 says, hey, can you actually solve for x? Can you actually solve arc sine equations? Remember, the idea is arc sine is the inverse. So to get rid of the inverse, you do the inverse of the inverse. Doing the inverse of the inverse just means I should take the sine of arc sine of x squared minus 3, which means I take the sine of pi over 2 on the right-hand side. Gotta do it to both the left and right. Doing that on the left just leaves me then with the function x squared minus 3. Calculating sine of pi over 2 on the right, that's equal to 1. Then, of course, this becomes x squared equals to 4, and x equals to plus or minus 2. And that's it. Alright. Now, let's see if we can show a visual representation of what an inverse sine can look like. And then from there, do example number 6 to actually find the derivative of inverse sine. So let's do examples 4 and 5 first. It says sketch a right triangle and then evaluate with a calculator, without a calculator. So they want you to find tangent x, but they just gave you this little piece of information. X equals arc cos of 2 over 5. Remember, if I want to get rid of the arc cos, I just take the inverse of the inverse on both sides. So that's really just taking cosine on both sides. And if you do cos of arc cos, of course, you're just left with the ratio 2 over root 5. So what you have here is cosine x equals to 2 over root 5. Now, how do I draw a picture for that? Well, if I were to draw a picture, here's my right angled triangle. My angle is now x. Cosine is defined as the adjacent side divided by the hypotenuse side. And then from here, I hope you can also find the missing length here using Pythagoras. I won't show you the work, but I hope you remember Pythagoras. A squared plus, I'll call it the question mark squared equals to root 5 all squared. That's just 5. 4 plus what gives you 5. The question mark is actually equal to 1. Okay. Now, once you've drawn your triangle like this, then you can go ahead and answer the question. The question in this example says, hey, tell me what tangent x equals to. And that's the ratio. So this is x. Tangent is defined as opposite over adjacent. So the answer for this question is just a half. Okay. Can you try the same idea for number 5? The only difference now is you're not given a value for the arc cos or arc sine. You're just given a variable, or x. But we do it the same way. So I will take the sine of y equals to arc sine of sine, that's just sine, which is x. So now in this example, what I'm saying to you is let's draw a picture where the angle is y. And remember, sine's definition is opposite over hypotenuse. So there's my opposite x. And my hypotenuse, of course, if I have x by itself, I can write it as a fraction by dividing it by 1. So the opposite is x. The hypotenuse is 1. Go ahead and find this missing side using Pythagoras. And I hope you will find that it's equal to the square root of 1 minus x squared. And so, therefore, if I asked you now to find cosine of y using this diagram is the adjacent side, which is root 1 minus x squared, divided by the hypotenuse, which is 1. So really, you don't need to divide by 1. There you have it. Okay. So why did I ask you to do example 5? Well, you're going to need it for example 6. So for example 6, I'm asking you to do the derivative of arcsine. So find the derivative of arcsine. So really what I'm saying is if my function is arcsine, go ahead and calculate the derivative. Find dy dx. Okay? Now, we do know derivatives for sine. So why don't I go ahead and just sine both sides? So once again, the sine of arcsine of x is just x. And now I'm given this lovely equation. Sine of y equals to x. Alright, I know you know implicit differentiation. Remember that stuff? So I'm going to ask you to implicitly differentiate both sides. The derivative sine is cosine. Our function is y, so you have an extra dy dx that appears. And the derivative of x is 1. So therefore dy dx is just equal to 1 over cosine of y. It's kind of weird that your derivative has a cosine of y. But what do we know is cosine of y? Say hello to example number 5. You got it. So, making that substitution, we know that this is just 1 divided by the square root of 1 minus x squared. And there you have it. You found the derivative of arcsine of x. It's 1 over the square root of 1 minus x squared. So, turn the page, dear friends. And now I want you to see a box of information that, of course, you need to memorize. So I just proved this from the previous page. Okay? You also need to know arccos, and using a similar proof, you'll be able to see that it's negative 1 over 1 minus x squared. And for arctangent, using a similar way to prove, you'll see that it's 1 over 1 plus x squared. Now these derivatives are only for x. Okay? Very simple x. But most of the time, you're not given x, but you're given a function. So note it, u is a function of x. So how do I find the derivative of arcsine of a function? It has the same form with the denominator, and instead of having x, you replace it with u, but there's this extra bit, the u prime, that appears in the numerator. It's really just chain rule. Okay. Same thing here, instead of negative 1, it's now negative u prime. And then for our tangent, once again, there's a u prime on top. Okay? So I guess if you're memorizing, memorize this one, because this actually works for all, including where x is equal to u. Okay? So, using these, now go ahead and find the derivative. Okay? So, derivatives, arctangent. So this is a function like u. So I'll use the formula here. I'll say g prime of y. The arctangent is just 1 over 1 plus the u, right? The u in this case is the 2y minus 1 all squared. And really, I have an extra u prime. So what's the derivative of 2y minus 1? Yes, it's the factor of 2. So 2 over 1 plus 2y minus 1 all squared. You are done. And in this case, I used this formula here. Okay. Notice for number 8, I'm asking you the arcsine of root x. Root x is x to the power of half. So the derivative here, I can use the sine function, or arcsine function, 1 minus root x all squared, with the derivative of that function, which would be this. And upon some simplification, I hope you can see that it's 1 over 2. X to the negative 1/2 is just the root x. And then you also have 1 minus x as another root. And that is your answer. I guess you could have combined it like this. Number 9, arc cos. So 1 over square root of 1 minus natural log of t. Notice I made a mistake. Arc cos is actually negative, so don't forget that. And then the derivative of the natural log of t is just 1 over t. So a lot of people write this as negative 1 over t, the square root of 1 minus natural log of t. And there should have been a square there. Got too excited, forgot little pieces. And then the last one for number 10. Hey, arcsine of x over 2. So once again, 1 over the square root of 1 minus x over 2 all squared. And then the derivative of x over 2, which is 1/2. That just seems to be 1 over 2, and this is 1 minus x over 4, or x squared over 4. Interestingly enough, if you want to simplify this a little bit more, I would then write the square root with a denominator of 4. And why would that be interesting? Because I hope you can see now that that's the same thing as 4 minus x squared over root 4. What's root 4? That root 4 is equal to 2. You're like, will this ever stop? Yes, it will right now, because 2 over 2 is just 1. So this is the same thing as 1 over 4 minus x squared. Okay. All is well? Good. Take a little quick break here before we do integration. Okay? Okay. Integration of inverse trig functions. Okay, so we just did derivatives, now we'll do integrals, and you need to memorize these as well. Notice the first one. It's really the inverse, or the integral of some crazy square root, and it becomes arcsine. So just going backwards. If I were to have a function where I have the u prime, or the derivative on top, and you see in the bottom, you have a square root of something squared minus another function squared. Notice, usually in these cases, a is the constant, and u is the function. Then we can just apply this formula. You get arcsine of u over a plus c. Same thing if you have a squared plus u squared in that type of form, then you've got this arctangent. So let's look at example number 11. Here's how I'd like you to integrate. Notice this looks very similar to number 1. And if you can quickly identify, I hope you can see that the a value is just equal to 2, because 4, of course, is 2 squared. And the u is just equal to x. And that's over here, right? So notice also that if u equals x, then I'll say note u prime just equals to 1, and that's great because that's the numerator that we have in question 11. So what does this all mean? It means I can directly apply formula number 1 and find my answer as the arcsine of u, which is x, over a, which is 2, and then plus c. And notice how arcsine of x over 2 is what I actually started with over here in example number 10. And you see how this was what I ended up with, which is what I started with, the integral. Haha, there was some reasoning to my madness of expanding and simplifying the answer to number 10. Alright, try number 12 now. So notice for number 12, you can see how this form looks more like number 2, because there's no square root. And I'm thinking, oh, that's a squared, right? So 25 is the same thing as 5 squared. I'm thinking a is equal to 5. And notice 4x squared is just 2x all squared. So I'm thinking u equals to 2x, which is good. But then if I take u prime, the derivative of 2x is 2, and I don't have a 2 on the top, and that might be a problem. Or is it? If I need to put a 2 on the top, that just means I need to multiply the numerator by 2. But to balance it out, I need to divide the numerator also by 2, or a half. Because a half times 2 is just 1. So really what I want us to do is rewrite this integral as 1/2 the integral of 2 dx over 4x squared plus 25. And now I can use this piece of information to just do a quick integral by using that formula. So now when I integrate, let's use the formula for number 2. It's 1 over a, so 1 over 5, arctangent of u, which is 2x, over the value of a, which is 5, and then plus c. So of course 1/2 times 1/5 is 1/10, arctangent of 2x over 5, and you can call it plus c or plus d, whatever you wish, doesn't matter. Okay. Alright, turn the page. So here are 4 more, and then we'll be done for today. Once again, if you look at 13, it has that form that looks like the arctangent. I guess a in this case is √3, and our u function is once again 2x. Once again, I want u prime to be 2, so this number here should be 2. Well, if it's supposed to be 2, then I can just make a 4 outside, because 4 times 2 is 8. And then I can just quickly apply the formula. So 4 stays there, and then remember it's 1 over a, so 1 over √3, arctangent of u over √3 plus c. Or if you want to simplify, 4 over √3, arctangent 2x over √3 plus c. Cool. Now, notice how the question for 13 and 14 and 15 are very, very similar. For 14, the only difference is instead of having 8, it's now 8x in the numerator. So if you are blindly thinking, let's do the same thing, where a equals √3, u equals to 2x, u prime equals to 2, so let's make this a 2, which means I need a 4x on the outside, and I go 4x like this. Sorry, can't do it that way. Right? Because you're really doing the integral of now not just a constant, this is a function. I can't just pull out the function. So, sorry. So don't get tricked up and think, oh, you know what? I've got this a squared plus u squared business. It has to be arctangent. The answer is no, it doesn't. Think back for this one as to what you can do. What other integrating techniques have you learned? way back. How about just letting u equal the denominator? What happens if I ask you to take the derivative here? Oh, yes, it's 8x. Oh, interesting. What's dx then? It's just du over 8x. Do you remember something called substitution rule, or called u sub? I hope you do, because that's what you see here. I've replaced the denominator with the u. The dx is now du over 8x. Ho, ho, ho. And then they divide out. Ho, ho, ho. The integral of 1 over u du, oh, ho, 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 is natural log of u, ho, 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 ho. And of course plus c. So let's replace natural log with 3 plus 4x squared plus c. Ta-da! So notice no need for inverse tangent integrals. Okay. How about 15? 8x squared this time. Whoa, whoa, whoa. So I can't use substitution rule. Boo-hoo. So another suggestion here to try to make this look nicer. These are little calculus tricks that you need to know, right? Like 14 with substitution. For number 15, the trick here is to do something we learned in Math 12, long division. If I were to take 4x squared plus 3 and divide it into 8x squared, notice the 4x squared goes into 8x squared twice. If I do the multiplication of 4 times 2, or 8x squared plus 6, and I subtract, notice I get a remainder of negative 6, which means I can rewrite this function as 2 plus the remainder, which is negative 6 over 3 plus 4x squared, all over dx. Why is this helpful? Because then I can integrate them separately. Integral of 2 dx minus the integral of 6 over 3 plus 4x squared dx. Okay. Integrating the 2 gives you 2x. Integrating this nasty beast is like example number 13. So I'll let you try that on your own. And once you do all the work, come back and check your answer with me. I'll give you a hint. U is actually 2x and a equals to root 3. Got it? Go for it. Don't cheat. I'm going to wait until you do it first. Still cheating, eh? Don't cheat. Try it. There you go. Your final answer. Did you cheat? Only you lose in the end. Alright. Last one. Save the best for last. You might be thinking, let's try substitution. Okay, just watch first. Let u equals to 4 minus x squared. Du dx, the derivative of 4 is 0. It's near 2x dx. That's cool, but wait a minute. Wait a minute. Oops. 2x, I should say. And then I should write down dx equals to du over 2x. And that's not so cool, because if I were to make that substitution here, I can't cancel out the x's. Boo-hoo. So, this one also has a special trick. Lots of tricks. tricks are for kids. No, they're for AP Calculus students. The trick here is to actually separate this into two rational or two fractions. See the x plus 4? I'm going to separate as an x divided by the denominator and a 4 divided by the denominator. Okay? Now, you should be able to try this. This part here, I'd be saying let's do a u substitution. This part here, I'm going to say to you, hey, this looks like an arc sine integral. And I know you know how to do both now. So guess what? You do this on your own. You get the response and come show me in class. And I'll give you a prize if you get it right. See you in class.